This section explores other important arithmetic functions, including contraction, incrementing, decrementing, and multiplication by constants, to name a few. These circuits can be implemented for multiple bit operands by using an iterative array of 1-bit cells. Instead of using these basic approaches, a combination of rudimentary functions and a new technique called contraction gets used. Contraction begins with a circuit such as binary adder or binary multiplier. This approach simplifies the design by converting existing circuits into useful but less complicated ones, instead of designing the latter circuits directly. The goal of contraction is to accomplish the design of a logic circuit or functional block by using results from past designs. It can be applied by the designer in designing a target circuit, or can be applied by logic synthesis tools to simplify an initial circuit with value fixing, transferring, or inverting on its inputs in order to obtain the target circuit. Let's take a look at contraction using Boolean equations. We'd like to make a circuit called add1. The circuit add1 is to be designed to form the sum Si and carry Ci plus 1 for the single bit addition A sub I plus 1 plus C sub I. This addition is a special case with B sub I set to 1 if the addition is performed by the full adder. We can make the new circuit by obtaining the equations and then simplifying them to get a simpler version of the equations. We can also perform contraction directly on circuit diagrams with rudimentary functions applied to function block inputs. In order to successfully apply contraction, the desired function must be attainable from the initial circuit by application of the rudimentary functions on its input. One thing we can do is we can perform contraction based on unused outputs. Placing an unknown value x on the output of a circuit means the output will not be used. Thus, the output gate and any other gates that drive only that output gate can be removed. These are the rules for contraction on unused outputs. There are similar but separate rules for contracting equations and logic diagrams. The rules for contracting the equations are listed here, and we'll look at the rules for contracting logic diagrams on the next slide. So as promised, these are the rules for contracting logic diagrams, and these are a slightly different set of rules. Let's spend a few minutes going over an example with incrementing. Incrementing means adding a fixed value to an arithmetic variable, most often a fixed value of 1. An n-bit incrementer that performs the operation a plus 1 can be obtained by using a binary adder that performs the operation a plus b with b is equal to 1. This figure shows a 3-bit adder with inputs fixed to represent the computation a plus 1. We can perform the contraction steps in our previous algorithm to obtain the increment function that's shown in this figure. There are actually quite a few things involved in this contraction. It's worth reviewing the detailed explanation in the text. We can also easily extend that process to work with an incrementer involving more than 3 bits. Decrementing is the addition of a fixed negative value to an arithmetic variable, most often a fixed value of minus 1. The contraction of the full adder in our first example can implement a decrementer. Alternatively, a decrementer could be designed by using adder or subtractor as a starting circuit and applying b equal 1 and selecting subtraction by setting s equal to 1. We can also use contraction to design a circuit that increments for s equals 0 and decrements for s equal 1. This figure shows a multiplier with 3-bit multiplier and a 4-bit multiplicand is shown with constant values applied to the multiplier. You can see the details of this design on the website associated with the text. Constants applied to the multiplier inputs have the following effects. If the multiplier value for a particular bit position is 1, then the multiplicand will be applied to an adder. If the value for a particular bit position is 0, then 0 will be applied to an adder, and the adder will be reduced by contraction to wires producing its right inputs, plus a carry of 0 on its outputs. In both cases, the AND gates will be removed. In this figure, the multiplier has been set to 101. The end result of the contraction of this circuit conveys the 2 least significant bits of B to the output C1 and C0. The circuit adds the 2 most significant bits of B to B, with the results shifted 2 positions to the left applied to the product outputs C6 through C2. Multiplication by 2 to the I is the left shift by I positions with 0 fill. Shifting is a very important operation and applied to both numerical and non-numerical data. The contraction resulting from a multiplication of 2 to the 2 is shown in this figure. Likewise, we can look at division by constants. Since multiplication of 2 raised to the I results in the addition of 0 i's to the right of the multiplicand, by analogy, division by 2 to the I results in the removal of at least I significant bits of the dividend. The remaining bits are a quotient, and the bits discarded are the remainder. The function of this block is called a right shift by I position. Just as for left shifting, right shifting is a very important operation. The figure here shows division by 2 to the 2. Zero fill, that is to say multiplication by a constant, can also be used to increase the number of bits in an operand. For example, suppose that a byte is to be used as an input to a circuit that requires an input of 16 bits. One possible way of producing the 16-bit input is to zero fill with 8 zeros on the left. Another way to expand our original number is to zero fill on the right. The former approach would be appropriate for operations such as addition and subtraction, and filling on the right would be used to produce a low-precision 16-bit multiplication result in which the byte represents the most significant 8 bits of the actual product, with the lower byte of the product discarded. In contrast to zero fill, the sign extension is used to increase the number of bits in an operand represented by using a complement representation for signed numbers. If the operand is positive, then the bits can be added to the left by extending the sign of that number. The reason for using sign extension is to preserve the complement representation for signed numbers. Thanks as always for watching. No like, share, or subscribes are necessary.